I'll just as well record this. So we're dealing with a question about the exam that's upcoming. No, I didn't call series name. What the heck is that about? So there's a carbocation called norbornyl carbocation with a positive charge there. And we'll talk about this in a minute, but this sigma bond ends up sort of migrating to be shared evenly between these two carbons. In sort of the same way we talked about it with cyclopropane. And I would not ask you to do orbitals for that one. That one's just too hard, too complicated to do sort of in your head. So something like cyclopropane that we've talked about, would you be able to deal with that? Yeah. Okay, other questions? Yeah.
Okay, so I guess I'm just like, we've done a couple different molecules, and I just have a hard time with deciding like which energy level is gonna, because there's kind of like a general rule that we worked with at the beginning, but then when we did like formaldehyde, like the pi CH2 to 2px was higher than the P plus P, and then
right.
there's also an example of this in the study guide, and I just don't know like how you are able to tell which one is going to be higher or not.
Okay, yeah, I agree that with ethylene, the sort of previous version, it's a little bit easier to keep track of things. The one thing that's sort of seems out of place is that these sigma outs, even though they're higher in energy than the pi CH2s, when they overlap in the plus combination, that end-on-end overlap is quite stabilizing, so that lowers it down below the pi minus pi type orbitals. But I'm sorry, but your question is for formaldehyde. Suddenly we are seeing the pi minus, I mean, in ethylene, this would have been the pi minus pi combination. Here is the pi minus 2p. Suddenly that's higher in energy than the 2p plus 2p. So that order is reversed. That would be tricky to predict. The only thing I think gets you there is the fact that your contributor from oxygen are these atomic p orbitals. And when you mix one with the pi CH2, the one goes lower and the other goes higher. So wherever this minus combination is, it has to be higher than the level of the p orbitals. In contrast, the 2p plus 2py has to be lower than those p orbitals. So that's where the switch occurs. Because for ethylene, the thing that you're bonding with the pi CH2 is another pi CH2, so it doesn't ever get up that high.
Yeah.
Okay.
And then just one more question
Yeah.
on that. Why is it that we had on that pi CH2 minus 2px, why did we have a majority of the electron density on the oxygen there? Good.
The reason for that is just what we showed back in chapter 14 with some calculations in the two orbital mixing problem, how when you mix two orbitals that are different in energy, the bonding combination is mostly on the atom that had the lower energy orbital, and the anti-bonding combination is mostly on the atom that had the higher energy orbital. So correspondingly for that, for the plus combination down here, we have more of it on the carbon because the carbon pi CH2 is lower in energy than the 2px. All right, cool. What else? You seriously don't want to ask me any other questions about the test? How long should it take you?
3 hours.
I would say, I don't know actually. I have statistics for the larger classes, and generally the average amount of time is about an hour and a half. But depending, you may want to plan for more or less depending on sort of your test taking style.
How many questions are you thinking there'll be?
4, maybe. I think there were 4, just like there were on. I'll plan on 4, just like there are on the problem set. they'll have subparts like A through Z, but you
Yeah.
know.
Of course. I mean, it's 150 points.
I'm so sorry.
Yeah.
Let's see. Oh, and so plan on, maybe an hour and a half plus or minus whatever window you want. Pay attention to the testing center hours. I think they're truncated on Monday nights because of family home evening, which has sort of been replaced by Come Follow Me, but sort of not. We're not actually sure what we're supposed to do.
Okay, so with the testing center, like if it closes at a certain time, I haven't been there. So
Yeah.
if it closes at 7, say they hand out the last test at 7,
Yeah.
is it an hour after that they just close the whole thing and they say get out?
So the hours that they will post will be when the last test is handed out, and you got an hour after that.
Okay.
So, for example, if it goes until 9 p.m., that means the last test is handed out at 9 p.m., and at 10 p.m. they come and make you leave. This early on in the semester, there shouldn't be too much there may not be a lot of lines. It sort of just depends on the day. You can go on the testing center website and sort of assess that. The one other thing that I hate that they make me do is that on the second day, the late fee kicks in at about 2 p.m. They do this, I used to have the option to waive the late fee, yes, but they do this because a lot of huge classes use the testing center and they need to manage crowds, and so they've done the math, and if they use a $5 late fee, then they can pretty well space out. Half the students will take it on the first day and half will take it on the second, because only about 50% of BYU students are willing to pay to take it later. So they enforce that to kick in on the last day of the test. If you find that this experience in the testing center is hellish, we can do something else. But that would require us to find some other time, probably in an evening, and you would just come here and take the test. So let's see how it goes, and then you can give me feedback depending on it.
Last question.
Yeah.
We're not going to need a calculator?
You shouldn't need a calculator. Should you need a calculator? No, I mean, maybe for that weird hybridization thing with the index, but no. Why would it would be pointless.
Okay.
Yeah. I'll provide a table of cosine values. No, I'm really not going to do that. Yeah.
So, in the example of the PyCH2 with the 2px,
Yeah.
are we also expected to know specifically that the orbital density is going to be mostly in the carbon?
You should know that, yeah, because the PyCH2 is lower than the 2px, when you make the plus combination, more of it will be on carbon than on oxygen. You're not required to know the extent to which that's the case, and we're not going to calculate any coefficients, just expect it to be biased towards the carbon.
Okay, cool.
Yeah. Okay. All right. Well, I want to talk about carbocation stability a little bit today. Last time we closed with the idea that the unique bonding situation with cyclopropane makes having a carbocation on an atom adjacent to a cyclopropane ring unusually stable for a primary carbocation. And the reason for this, we said, was overlap of one of the highest occupied orbitals on cyclopropane with the empty p orbital on that CH2 carbon, or the interaction of the 2py orbital from a bent CH2 with the group orbitals for cyclopropane. And this is the LUMO. This shows the positive charge being delocalized onto these carbons. This is the unoccupied orbital. For the occupied version, we would simply have to change the phases, and this allows the electrons in the highest occupied orbital of cyclopropane to spread out into that nearby p orbital, and that's a stabilizing effect. Okay. In terms of how valence bond theory deals with this, it's a bit of a challenge because you have to do something that you may not be used to, and that is sigma bond resonance structures. Typically with resonance structures, we're moving pi bonds in lone pairs, but there are some cases where you got to deal with sigma bonds. And so we showed how you can show moving this sigma bond up to make a new bond with, we'll call it carbon 4 for the sake of our discussion, be now between 1 and 4. You can do the same thing with the bond between 2 and 3, shift it up to form a bond between 2 and 4. And then you can actually make a pi bond between, sorry, I'm spacing, 3 and 4, thank you. So if we were to draw a hybrid structure, and you would need all of these resonance structures to really discuss or really describe the behavior of this molecule. If you drew a hybrid structure, you would have, it doesn't matter, 1, 2, 3, and 4. You would have carbon 2 bonding with both carbons 3 and 4. Carbon 1 bonding with carbons 3 and 4. Carbon 4 bonding with carbons 1 and 2. So if you look at, and maybe it would be helpful to fill in the hydrogens that are implied but not shown here. You have really, in this story, a carbon that's bonded to 1, 2, 3, and then partially bonded to 4 and 5 things. So a situation where a carbon is interacting with more than 4 things, we call that a hypervalent carbon. And these are sometimes called non-classical carbocations. And the real question that has incited lots of controversy in physical organic chemistry is whether these are indeed resonance structures or whether they are in equilibrium with each other. And the answer is controversial, and it probably depends on a case-by-case basis. Carbocations in which you have at least one atom that's interacting with 5 things, we typically call those carbonium ions. Regular carbocations, I didn't actually know this till I taught this class, are sometimes called carbenium ions. So that's another dumb thing you got to remember based on the change of one letter. Carbonium is a carbocation involving a hypervalent atom, like a carbon or a hydrogen, and carbenium is just your regular carbocation. So as an example, right, just to compare, if we looked at these two species, this one would be carbenium, and this is probably carbonium based on what you know about the ability of the cyclopropane ring to interact with the positive charge on that adjacent carbon. Another interesting example of this issue of hypervalent atoms comes if you do experiments and or calculations on ethylene carbocation. All right, C2H5 plus. We're not going to worry that this is a primary carbocation. This is in the gas phase, so who cares? Now, you probably learned in 351, or if you're TAing for 351, you may be about to share this with the students, that carbocations can rearrange. And you may have before drawn an arrow like this in which the hydrogen leans over with its electrons and then makes a new bond with carbon 2 and breaks its original bond with carbon 1. And at this point, you may be saying, those are both identical, the two carbons. It's just like, why are we doing this? Well, stay tuned, because this is even if the reaction is inconsequential, the rearrangement is possible. Now let's think about what the transition state for that reaction might look like, where a hydrogen was maybe partially bonded to 1, and maybe partially bonded to 2, and sort of hovering over in the middle. Okay, so we got these 3 sort of structures, A, B, and C. And a question you could ask is, if you do the math and make some measurements, is B a transition state? And I guess we would have to put partial positive charges here and here. Is B a transition state, or is it an intermediate? Notice what B is. You have a hydrogen interacting with 2 things instead of 1 thing. You have 2 electrons being shared between 3 atoms. Your text calls this a 3-atom, 2-electron bond. This would be another example of a carbonium ion, because you've got a hypervalent hydrogen. It's bonded to more things than it should be. All right, so is it a transition state or an intermediate? When we ask that question, we're basically asking whether the energy diagram looks like any one of these options. So one would be A, B, and C. Oops, sorry. Right, where A is a carbenium ion, C is a localized carbenium ion, and then B is the transition state. Or you might imagine that you could go from A to an intermediate down to C, and maybe B is, instead of at a maximum, maybe it's at some minimum. Or alternatively, you could imagine that the real stable situation is that maybe maybe A and C are actually higher in energy than B. Maybe B is the sort of resting state. Or actually maybe A and B are so high in energy as to be negligible, and the only thing that matters is C or B, right? A and C, maybe A and C are actually energy maxima or something like that. So this is sort of the debate with carbocations. Is this B carbonium a transition state, or is it an intermediate, or is it actually the most stable carbocation? If you think about, and if you looked at either of these, A, B, and C, you could think about what orbitals are interacting from a group orbital theory point of view, right? And the answer for ethylene is that probably B is the most stable. So it's probably, for C2H5+, its lowest energy arrangement in the gas phase is probably that bridged ion. Though, yeah.
Get the positive charge on the hydrogen, the partial positive on the hydrogen.
On the hydrogen as well? Sure. And if you thought about the orbitals here, this would almost look like a 1s orbital on hydrogen sitting down on top of a pi bond. Yeah.
So does that mean for the energy diagram that you just circled, so if we're thinking that that's the most stable, like B is more stable, then we're looking at is that looking at it as an intermediate and not a transition state?
That's right. If B is the most stable one, it's not a transition state, it's the intermediate. And actually, it's not even the intermediate, it's the starting material / product.
Okay. Why would it be a 1s orbital sitting on top of a pi bond? Why would the pi bond?
Well, let's think of it this way. There's two ways to think of this. Think of how you even get to CH2, C2H5. I mean, this, in the gas phase, this is sort of how you would do it. You'd have HOMO of ethylene, the pi system, or the pi bond, the P plus P orbital. And then you would mix that with the 1s orbital on hydrogen. And it would overlap in phase. You can get to oops, I guess I'll just leave that there. You can get to roughly the same conclusion if you construct this carbocation with a pi CH2 and a 2py orbital on carbons 1 and 2 respectively. And then over here it's a 2py orbital with a pi CH. I'm sorry, did I say CH through 2? I guess I meant CH3. And in the middle, it's something in between, almost as though you have sort of 2p orbitals and the s orbital on hydrogen. Okay. The moral of the story, though, is that it's not always the bridge species, and that these potential energy surfaces for carbocations are relatively flat. The difference in energy between A and B is small. So prepare for carbocations to rearrange, and prepare for that to be important in various chemical and biological processes. All right. So carbocation stability. All right. Your text in chapter 2 spends a lot of time telling you how to calculate bond dissociation energies. I spent some time talking about that last year, and then I instantly regretted it. So don't worry about that part of chapter 2. In terms of carbocation stability, be able to rationalize trends. So I'll pull some numbers off of a table, and based on things that we've talked about, and you can maybe give me an explanation as to why. This is one that we just did, but I'll put some numbers on it. For carbocations, we're going to write down hydride affinity values in kilocalories per mole. These are gas phase numbers for how much the carbocation would like to react with a hydride. So you've got quite a difference between cyclopropane and the non-cyclic version, and that's accounted for by the resonance that we talked about with these sigma bonds and that positive charge. Let's see. You've got the classic comparison that you maybe have taught students about already, secondary versus tertiary. Why is that? By the way, tertiary is more stable, has a lower hydride affinity. Why is that? Okay.
Reduction from like 3 different carbons.
Okay, so you've been taught that sp2 carbons are more electronegative than sp3, and therefore sp3s donate to sp2s, and the more sp2s you have, the more you can donate into that positive charge. Okay, that's decent. And that's fine. There's a deeper explanation that depends on orbitals. I was toying with writing a test question about it, but I'll just tell you. So imagine a carbocation like, let's see, what do we want to do? I don't really. Oops. And I'm going to just draw out, well, this will be the secondary carbocation. I'm just going to leave one methyl group out there. We're only going to think of two things. So if you think about group orbitals, you know that if you're going to treat, and maybe we'll just do this with the ethylene and then we can extrapolate from that to other things. We could make this carbocation by combining pyramidal methyl and bent CH2. And we won't do all of the bonds, but one of the combinations that would work would be the pi CH3 which comes from a 2py orbital on the carbon overlapping with the hydrogens on the methyl group, and then that has the right symmetry to overlap with the 2py orbital on the bent CH2 group. And they can overlap in phase. Here's the plus combination. And then you could similarly draw the minus combination, which would simply have the wave function signs reversed with a node, in the middle. I need a minus there. Okay, so think about, and this orbital will end up being filled, whereas this orbital will be empty. What happens when you mix two orbitals together in the plus combination? Are they higher or lower in energy than they used to be? Always lower, right? Bonding orbital. So those, and it's true that the antibonding orbital is higher in energy than either of those orbitals used to be, but that doesn't matter because this is the one that's filled. So when you have alkyl groups adjacent to the positive charge, you actually spread out electrons from these CH bonds into the area where the positive charge is. And the more alkyl groups you have, the more you can do that. The more bonding interactions you have with that positively charged carbon. The more you spread out those electrons, the lower in energy you go. These are still very reactive, but they get less and less reactive the more alkyl groups you have nearby. Now, that's our sort of QMOT approach. The valence bond theory approach invokes something called hyperconjugation, which you may have heard about before. Hyperconjugation technically is related to the following no-bond resonance structure, in which we simply shift the sigma bond down to make a pi bond, and then proton hangs out by itself up there. But that describes the ability of that carbon-hydrogen bond to donate electron density into where the positive charge is. Another way of thinking of this in a somewhat hybrid valence bond and MO theory approach is to consider that you have an empty p orbital on the positively charged carbon. And then on the adjacent carbon, you have a bonding orbital between an sp3 orbital on carbon and a 1s orbital on hydrogen. And you have this filled orbital overlapping with an empty orbital and delocalizing its electron density into that empty orbital. That should make these electrons go down in energy, and it should also spread out the positive charge. So this concept is called hyperconjugation. And whether you want to think about it that way or the Q-Mott way is fine. You can sort of see how they're roughly equivalent. Okay, questions about that and carbocation stability? Okay, let's do a few more. Sorry, I'm struggling to figure out what exactly we want to do. Tertiary carbocation, hydride affinity 231. This is also a tertiary carbocation, but it's 220. What's the difference there?
There's resonance structure with the ring.
Resonance with the benzene ring, and in fact, yes, you could draw several resonance structures in which that positive charge was spread out onto either of those carbons. Okay, and in general, the more places you have to spread out the positive charge, the more stable that carbocation can be. There's some subtle effects that I think we probably don't need to necessarily go into. Another interesting comparison is between this 7-member. Why can't I do this? I'm usually very good at drawing a 7-membered ring. Versus this one. This one has hydride affinity of 201. This one has hydride affinity of 258.
Also aromaticity, right? Because the one on the right is going to be antiaromatic.
Right, aromatic versus anti-aromatic. And we may talk about more about what aromaticity means later. But yeah, this has enough electrons. In aromaticity, you've got one lower energy orbital and then degenerate pairs of higher energy orbitals all the way up. And in aromaticity, you just fill, if you have the right number of electrons, you just fill the bonding orbitals completely and none of the anti-bonding orbitals. If you only have 4 electrons in an aromatic system, then if you stay that way, you're going to end up with 2 partially filled orbitals. Okay. And it turns out that if you look at the stability of just a non-resonance stabilized secondary carbocation, it's actually more stable than that carbocation. Okay, and sometimes these anti-aromatic carbocations will distort themselves so that they are no longer anti-aromatic. And evidence for that, I think, is related to the fact that if you just take this carbocation that's resonance stabilized, its hydride affinity is about the same. So this secondary anti-aromatic carbocation is about as stabilized as this primary resonance stabilized carbocation. Yeah?
But if that was a secondary stabilized
Ah.
it would be
What if? So let's do that. Positive charge here. That one is 225. Yep. Yeah.
And so just like you said, so when they're anti-aromatic, because they want to be more stable, they will distort themselves, right?
Right.
How
They can
does
distort
that
themselves
affect-
from planarity by,
Right.
you can imagine this CH2 group swinging up to be conjugated with one, but maybe not both. Anyway, kind of some interesting effects. Now, the 351 or undergrad sophomore organic student inside you wants to know, how much of this do I need to be able to predict? will I need to be able to predict that? And we get these questions all the time. So what about the difference between these two carbocations? How much is it and what should it be worth? There are actually things like this found on the table. If you want to know, this carbocation has a hydride affinity of 225. So tertiary on one side and primary on the other is about the same as secondary on both sides. Probably don't need to memorize that, but be able to rationalize differences like we've talked about today in examples that I show you. All right, carbocations. I guess I want to show you one more set just for fun, since we could go on and talk about conformations and angle strain. You've done some things in your calculations on that. I think I got enough fish to fry. I don't think we're going to talk about conformations and angle strain in the exam that will be ready for you on Monday. But let's do one last example. So here is a bicyclic system, Norbornyl carbocation. It's like having two 5-membered rings that share two sides, or like having a 6-membered ring that is bridged across the middle by a CH2 group. So it turns out, and I did some calculations on this the other day, it turns out the structure of this molecule is not necessarily like I showed you. This bond between carbons 2 and 3 is actually really short. It's quite shorter than you would expect for a single bond. And the rationale for this is that the real structure of this carbocation involves partial double bond character there, involves this sigma bond moving over. And so this is an example of a non-classical carbocation. We could draw resonance structures in which carbon 1 was bonded to carbon 3. This gets crazy, huh? Go ahead.
So sorry, I just want to say that if we do that, then the carbocation comes to carbon 2?
Yes. Yep. Oh, hold on. Sorry. This bond would still be there, but we've moved it over, so there we go. And then yeah, and then you could also draw a resonance structure in which you just had a double bond there and a positive charge on that carbon. Yeah.
So why is the 2-3 bond shorter than the 1-2 if the 1-2 is being the one that's taken off? Is it because of that pi?
The 2-3 bond is shorter in order to bring 3 close enough to 1 to do this.
Oh, okay.
And also, yes, because that bond has some partial double bond character. The MO picture here is really wild, so we're not going to go there. The hydride affinity for Norbornyl carbocation is 231, and that's on a secondary carbon. So compared to other secondary carbon type things, resonance structure and secondary carbon, I don't know what an example might be. Maybe this one has a hydride affinity of 225. So this certainly falls into what you would expect for a pseudo-resonance stabilized carbocation. And what that tells you is that, based on the hydride affinity data, if Norbornyl carbocation looks like it's resonance stabilized, probably the carbonium ion is the right structure. Now, a funny thing happens when you do take the same molecule, but now put a methyl group on carbon 3. Now, hydride affinity goes to 225, but compared to a regular non-resonance stabilized tertiary carbocation, that's 231. So this one is probably localized. See what we're doing? We're comparing tertiary here with tertiary there. Maybe that's not the best model compound, but it's close. And we could look at a case of, let's see, do we have an example of tertiary carbocation on both sides for resonance? Not really. So that's hard to make that comparison. But it's in the ballpark for what you'd expect for a tertiary carbocation. In contrast, if this were a localized secondary carbocation, we would expect hydride affinity to be like 246. So this is no longer in the ballpark. This is quite a bit lower. You see I'm not sure I've explained that. See the reasoning here? Secondary carbocation in the Lewis structure of norbornyl is much more stable than just a localized secondary carbocation, and in fact it's pretty close to what you would expect for a resonance stabilized secondary carbocation. In contrast, when you put a methyl group there, it looks like it behaves more like a regular tertiary carbocation. And I presumably, maybe I'll run upstairs and do this, we could do the calculation adding the methyl group. Presumably that bond between 2 and 3 would be a little lower. A little less like a pi bond, a little bit more like a regular sigma bond. That could be cool. Maybe I'll do that. Actually, I should be writing your test. All right. Sounds good. Have a good day. Hang in there. It's going to be okay.